Program synthesis considers the problem of generating executable code from some sort of high-level declarative specification. Synthesizers have come a long way recently and can generate programs performing non-trivial data structure manipulations. For example, we can ask for a program that finds the intersection of two sorted lists and get a provably correct recursive function. The problem is that the shortest implementation of this function runs in quadratic time with respect to the length of the input lists. There is a faster implementation that leverages the sortedness of the input lists to find their intersection in linear time. However, synthesizers cannot differentiate between slow and fast implementations of the same specification, instead tending to return the shortest version. We need a synthesizer that can generate efficient code. We want to be able to tell the synthesizer to implement a function in linear time and get back the efficient version. To address this problem, we present Resin, the first resource-aware synthesizer for recursive programming.
A typical way to look at program synthesis is that the user provides a set of input-output examples and gives it to the synthesizer. The synthesizer then generates a program that satisfies the examples. A problem here is that the examples often underspecify the program behavior and that they are not necessarily easier to write than the program. So instead of using input-output examples, we use a program as the specification. We can use active learning to infer the program and regenerate a new one that does the same thing. To infer the program, we treat it as a gray box. We know that the program has several components, and we observe the traffic between them. We are often asked the question, if you already have a program, why do you synthesize another one that does the same thing? To find out the answer and how we do this, read our paper or come to our talk.
Hey, Kostas, what's happening? I'm going to need you to come in tomorrow before you go to PLDI. We have a new database schema and need you to write a new program. Okay? Okay.
Kostas, new schema, blah, blah, blah. Okay? I'll never be done before PLDI. Hey, boss. I'm finally done with the program.
That's great. But did you get the memo? We changed the schema again. So when you get back from PLDI, if you could implement a new program, that would be great. Okay? Okay.
So in conclusion, we can use Migrator to synthesize a new version of a database program in a matter of minutes.
Wow, that was so easy. Migrator synthesized the program in a jiff. I'm so glad that I attended that PLDI talk. That was great. High five, boss.
Say you need to extract some reservation numbers from thousands of flight reservation emails. The main issue here is that there are hundreds of different formats of these kinds of emails, and that new formats keep appearing over time. This makes it really quite a hard problem. Classically, there are two ways of approaching this. Option one is you can train and use ML models. I really think of ML models as a mad scientist. He's really, really clever. So if you show him what to do on one or two different formats, he's able to generalize reasonably well to all other formats. However, he's obviously too busy and too clever to explain exactly what he's doing. The other option is to use program synthesis to produce programs. This is like your friendly neighborhood doctor. He's super methodical, so if he gets something right once, he gets it right every single time. And he's also really, really friendly. He explains and documents exactly what he's doing. So if you come to my talk on Monday at 3 p.m., I'll explain how exactly to get these two clashing personalities to work together, and also how to do heterogeneous data extraction using program synthesis and machine learning.